In the last video, we introduced differential equations and talked about solutions and solution types and introduced the terms boundary value and initial value. In this video, we're going to apply all that stuff through the technique called separation of variables. So in Module 4a and 4b, we already discussed how to solve differential equations like this. So we would integrate both sides, or determine the antiderivative of both sides, and we know the antiderivatives of these basic functions. Now what we want to do is look at what if we don't have nice rate of change equations or differential equations like these. One technique that we can try is called separation of variables. So what we're going to do is first get all the variables of one type to one side of the equation and all the others to the other side. Okay, so here we have, and this should say g of y. So what we want to do is we want to get the functions containing x to one side and the functions containing y to one side. So here f of x stays on the same side, and I move dx to the other side. Here, with g of y, I move that to the other side, and possibly when you do that, you may change it, or change the function. You probably will, actually, and so that's why I call it h of y. Same idea as before. And then once we get to this point, then what we're going to do is we're going to integrate with respect to the variable appearing on that side. So, for example, this side contains only y, so I'm going to integrate that side with respect to y and that side with respect to x. Okay? So I'm going to integrate, and then pretty much just from there it's just algebra. So remember, we typically use capital letters to determine or to denote the antiderivative. So this just means the antiderivative of y equals the antiderivative of f plus a constant. Okay, and so remember, this constant makes up our general equation, or our general solution. Okay, so let's go ahead and see this in practice. So we want to find the general solution of the differential equation like this. Okay, we have y and t, so get y on one side and get t on the other. So I'm going to move this y over to that side, and I'm going to move the dt over to this side. Okay, so I have to multiply by y squared on both sides, and I'm going to multiply both sides by dt. When I do that, the dt's cancel over here, and on the left-hand side I'm left with y squared dy is equal to minus 2. dt goes in the numerator over e to the minus 4t, and I'm going to rewrite that side just because I don't like negative exponents. Whenever I can, if I can avoid them, I want to. So I'm going to write this as minus 2e to the 4t dt. Okay, and now, so I have my variables separated. Now I'm going to integrate. Okay, and let's see, the antiderivative of this side is y cubed over 3. And the antiderivative of this side is going to be e to the 4t, that doesn't change, minus 2, and I have to divide by 4 due to the exponent, or due to the coefficient of t, and then add my constant. Okay, and at this point you're pretty much done. If you want to solve for y, we can do that quickly here, and you're going to get 1/2 times 3, so I'm going to say that's minus 3/2 e to the 4t, and I'm going to label this as plus c star. Okay, c star, really what that just means is you have your constant of integration, and then you would multiply by 3, but that's really just another constant, so that's why I call it c star. And then lastly, if you wanted to solve for y, you would cube root everything, or write everything to the 1/3 power, which is what I'll do here, to the 1/3. Okay, and that's the general solution, because in the general solution, remember, we have an undetermined constant. Okay, idea pretty straightforward. Separate the variables, integrate each side with respect to the variable appearing on that side, and then just walk through some algebra. Okay, and really at this point, this would be an okay answer. And in fact, there's a problem in WebWork. I think it has like y to the 11th that will have this form too. So you can just leave it like that. Now another problem where we want to find the particular solution, and now in the particular solution, remember you have a condition that accompanies it, or accompanies the differential equation. So let's go ahead and walk through this. So we're going to find the general solution first, and then apply this condition to find the particular solution. Alright, so separating the variables, I'm going to divide both sides by y, and remember this side is a dy over dx, so I'll also multiply each side by dx. So I end up this side equaling dy over y is equal to 3 sine of 4x plus, times dx. Okay. Next step is to integrate. So this side, the antiderivative natural log of the absolute value of y is equal to, and this side is going to be minus 3/4 cosine of 4x plus c. Okay, and now I'm going to solve for y. So I'm going to remember I can switch this from logarithmic form to exponential form. So e to the minus 3/4 cosine of 4x plus c. Okay. Now I can apply my initial condition, but I think it'll be easiest if I do a little algebra first. So what I'm going to do is write this as e to the minus 3/4 cosine of 4x times, now, and remember by laws of exponents, I can write this as e to the c. Okay, and I'm going to take c star to be e to the c. C star, remember, is just another constant, so take that equal to e to the c. Y is equal to c star e to the minus 3/4 cosine of 4x. Okay. Now, up to this point, it's just been algebra. Now I'm going to apply my initial condition, which was y of pi over 4 is equal to e to the 3/4. Okay, so let's see, if I put that stuff in, I should get e to the 3/4 is equal to c star e to the minus 3/4 cosine of 4 times pi over 4. This side changes to e to the minus 3/4 cosine of essentially pi, which is times minus 1. Okay, and I'll leave this for you to show, but the e's to the 3/4 cancel, and you're gonna, or divide out, and you're gonna be left with c star is equal to 1. So that means that my solution, my particular solution, is y is equal to e to the minus 3/4 cosine of 4x. Okay, because the c star was just 1. Okay, and that will be my answer. Same idea as what we did with the particular solution, except now that, or with the general solution, except we applied that initial condition, or the boundary value. I'm sorry, the boundary value. Alright, application. So in a quantity that follows exponential growth and decay, the change in the quantity, so I'm going to denote that as dA dt, is proportional to, so k to the amount of the quantity. So Ka. And K here we call the rate constant. Now remember, if we have K greater than 0, that's growth, and if we have K less than 0, that's decay. Okay, so we can actually see that this differential equation can be solved by separation of variables. I can get the A's together, and the T will be our other variable. So what I'm going to do is go ahead and solve this. And we do this in the notes. Feel free to reference that as needed. So separating this, I get dA over A is equal to k dt. And so going through this, integrating each side, I get ln of the absolute value of A is equal to kt plus c. Okay. And then again, following that same idea as what we did in the last example, solving for A, I get A is equal to e to the kt plus c, okay, by switching it to exponential form. And then lastly, rewriting this, I can write this as A is equal to c star e to the kt. Alright, but there's one more condition that we have to satisfy. At time 0, the quantity is given by A naught. So going ahead and solving this, this is A naught is equal to c star e to the 0. E to the 0 is just 1, so that means that c star is equal to A naught. And thus, our solution, which we already know, is the solution to this differential equation is A is equal to A naught e to the kt. Okay, and I'm not going to have time to go through an example of this in the video. There are examples worked out in the module notes, and I strongly encourage you to reference those because there are a couple other examples. An example about half-life, which is a time value where you have 1/2 of the original quantity remaining. And then there's also an example on Newton's law of cooling. Alright, so this has been a basic introduction to separation of variables. We will hopefully get some more practice on this in class and in web work.